Hey guys, you are on A-Level Maths. This is revision and this is new syllabus for 2020-2022. That's the latest updates. We're gonna go through integration topic from pure maths, and that's we particularly consider numerical integration, the trapezium rule. We're gonna go through the basic principle of integration and numerical integration, that you can approximate the value of definite integral using the idea that definite integral is the area under the curve. So we actually we'll be trying to approximate the area under the curve using different shapes. So as you remember from Riemann sum, from definition of definite integral as the limit of Riemann sums, and Riemann sums comes from the idea that you can approximate the area under the curve by circumscribing or inscribing rectangles, so that it indeed will give you an estimation for the area. So in this case, for example, you can use the left endpoints values for y's, and here you are going to use the right endpoints values for your function. So the idea is pretty straightforward. So any random rectangle and area consequently can be calculated using the area of rectangle with size of delta x, that's the width, right, and the height equal to the value of the function. So indeed, if you take, for example, that length is going to be f from xi, given point xi here, okay? So that's why that's going to be the area of rectangle, and to sum up the area, you finally will come to the idea of integral, definite integral as the limit. But in this case, we actually know that number of rectangles that you circumscribe or inscribe should be infinite big. Like ideally it's going to be n equals to infinity. But what if you have finite number of rectangles, like in this case 1, 2, 3, 4, 5, 6? So in this case the idea of estimation takes place. So integral from a to b fx dx is approximately the sum of all partial areas I from 1 to number of intervals that you split. And that's the estimation, as you remember from Riemann sums. Let's go to trapezium rule and try to understand how the trapezium works here. Okay, so the idea is the same. You need to inscribe the shape. In this case, the shape is trapezium. Why? Because if you notice, for example, for that part, you see that if you connect y1 and y2 value by a straight line, actually you will have better approximation. So your curve and your straight line from your straight line segment from y1 to y2 is actually pretty match or pretty coincide to each other. That's why trapezium rule will give better approximation in comparison with rectangle and Riemann sums that comes from rectangles. Actually, you see those parts actually overestimate the area and those parts underestimate the area. So you have those gaps, and that's why in comparison with trapezium rule it looks like much better. All right, let's go to the idea. So let's assume we split up by seven points, and actually we have 1, 2, 3, 4, 5, and 6 intervals, and let's say that the length for each interval is delta x. So let's say it's constant. Let's pretend that we're going to use constant height of the trapezium, because actually it looks like height. So how we can estimate the area, or how we, first we can calculate the area of the trapezium. So using the height, and two bases actually will correspond to the values of functions and given points. So in this case, we're actually taking y5 and y6, okay? So it means we're taking the function f from x5, and here we go on the value f from x6. So that's how we can get the basis. So for the area, we have the formula 1/2 sum of the basis and times the height. So that's particular area for a given trapezium under the function. If we sum up, we actually get the following formula. For example, for those cases when we have 1, 2, 3, 4, 5, and 6 trapezium, we'll get 6 terms, and each term will represent a particular area of each trapezium. However, it's long-wise. Maybe if we can rearrange this formula, we'll get the shortcut, or what actually is called Trapezium Rule. And indeed, if you, for example, separate, first of all, you factorize 1/2 delta x. So that's the common factor because it's common everywhere. And also you notice that y1 and the last value, y7, they are single, they are not repeating. While, for example, if you go to y2 here and y2 here, you can add them up. So that's why you'll have double term from y2 up to y6, because y6 is the last y value that has the couple. So in this case, we'll have y2, y3 up to y6, the double. So that's actually the shortcut for the area for 6 intervals. That's for 6. What if we generalize the formula and try to apply it to, let's say, n-1 interval? In this case, we will have that works for, so that works for not n's but n-1 interval, because number of intervals 1 less than number of y values. So that's why we can generalize the formula for 7 y values to n y values. In this case, we just simply need to add the first y with the last yn and to add double sum of all interim intervals or interim values in between them. So that's how the general formula works. Okay, and let's go to exam style question from Edexcel. Let's try to find out how it works. So this is the question, so pause the video, try to do by your own, and let's get started solving. Okay, so we have the speed that arrange and can be calculated using the following formula: 1.5 to the power 1 to t minus 1. So t intervals from 0 to 15. And first, we need to complete the table given the values for v to 2 decimal places. Alright, so let's go and use calculator and just plug the values for t from 9 here to 15 with a 3 seconds interval. Means we have actually delta t equal to 3 seconds. Okay, use calculator. Let's do it. We just plug the t9 into the formula, and that's how we can calculate. Then we round to 2 decimal place. 887, next one 18.50, and the last one 38.43. Okay, next one, we have all values for v and we have all values for t from 0 to 15. Now we have the distance that can be figured out as integral v from t dt. Actually, just remember mechanics course, how you can calculate distance if the speed is not constant. Alright, so you need to take integral. In this case, in 50 seconds, we are going to use the limits from 0, that's lower limit, and upper limit 15 seconds. Okay, it's right there. So we use that formula, but however, unfortunately, we cannot integrate, so that's why we need to use Trapezium Rule with all values from the table, and now we need to estimate d. Okay, So let's write a formula for the area, because in this case distance is actually correspond to the area on the curve v from t. So that's simply the same. And we're going to use trapezium rule. So let's just remember and work out how the formula works. So the formula works as area, in this case I'm going to use distance is simply 1 over 2 delta t. I'll just write using those notations. So in our case the width is delta t equals 3 seconds, and we multiply by v from t1 v. So how many values we have? 1, 2, 3, 4, 5, 6. We'll have 6 values. In this case we're going to use 6 intervals. Okay, so that's why it's v from t1 plus v from t6, while here we need to add double sum of v from t2, v from t3, and v from t4, and the last one is v from t5. Okay, so that's how the formula will work for our, because that's the first value, this is the last one, and this is the interim sum of all values that we have here. Alright, so we'll just pick the values from there and plug into the formula. So we will have 1 over 2, so interval is 3 seconds, and there we just use the values from the table, okay? But I'm going to use shortcut. First of all, I'll add v from t1 and v from t6. Actually, I'm grabbing that and that, so we'll use 38, 43, and then I also calculate the double sum of all other terms. So double sum will give me 66.76 meter per second. And now we just simply need to multiply that, and finally we will get the distance equal to 157.79 meters. That's how we can use and apply trapezium rule, and I hope you understand the high resemblance trapezium rule with the general principle of integration and approximation using Riemann Sums that actually you need to cover before. Okay, that was Daniel Dallas. Thank you guys. Make sure you actually check the A-level resilience class. He also explained trapezium rule, checking them out. He also provides some examples. So here I'm going to continue giving more examples and more exam styles questions for you guys succeeding in your final exams and mocks. Thank you. I was Daniel Dallas. See you later.